First thing I'm going to talk about is an idea called differentiability. Okay? Basically, all we need to know is this. In order for a curve to be differentiable, it must be what we call smooth continuous. So I guess the first key point is continuous. Smooth because it can't be like, say, the absolute value function. Because remember what we've now discovered that the derivative measures. When we're talking about graphs, it's measuring the slope at a particular point. So if you think of your absolute value graph at the v point, what's the slope of the tangent at that point? Well, you got two different answers because of the v shape. It's not smooth. So really, we only need to look at a graph and we can see whether it's smooth or continuous. The formal definition is this. Similar to the continuity definition, but this time looking at the derivatives. If you were to look at the slope or the derivative coming from the negative side, and if that was the same as the slope or the derivative coming from the positive side, then that would be smooth continuous. So here we go, that's what I was talking about. Here's the absolute value curve. If I was to look at the point where x equals 1, it's not differentiable because it's not smooth continuous. It is continuous, certainly not smooth though. You've got that sharp corner to it. Right? So from a technical point of view, the limit from the left-hand side would be -1 because the slope of the left-hand branch is -1, whereas the right-hand side it would be +1. So not the same as opposed to, say, a parabola. But if I was to look at, say, a similar point, x equals 1, differentiable at x equals 1, yes it is. Because if I was to go, from the left-hand side or the right-hand side, I'm still going to get that same slope. It's a smooth curve. So as I say, from our point of view, the only thing we really need to know is look at the picture. Is it smooth? Yes, it's differentiable at that point. We don't really need to worry about the formal definition. Okay, the other thing to look at today is this thing called implicit differentiation. It's really the chain rule. Or rates of change. It's the same idea. If I want to differentiate a function with respect to x, but I can't, I can differentiate it with respect to something else, say y, not a problem. I'll differentiate it with respect to y and multiply it by dy dx. And that'll, the dy's, if you like, balance out. And what that allows me to do is, say x equals y squared, all right, not a hard thing to make y the subject. But say I didn't want to make y the subject, and I still want to find dy dx. You've got to think of it like an equation. What technically we're doing when we're differentiating is we're saying, I'm going to differentiate both sides. Now, on this side, when I differentiate x with respect to x, I'll get 1. And on the right-hand side, well, the right-hand side I've got a problem. I can't differentiate y squared with respect to x, but I can differentiate it with respect to y. So I'll do that, but then multiply it by dy dx. So I get an answer of 1 equals 2y, because that's the derivative of y squared with respect to y, times dy dx. And then I can rearrange this, and I've now got a formula. The difference here is instead of substituting in the x value to find the slope, I'll substitute in the y value to find the slope. Something like x squared y cubed, if I want to differentiate this with respect to x, I've got two things multiplied together, so I'm going to have to use a product rule. Write down the first, x squared, diff the second, y cubed. Well, hang on, I can't differentiate y cubed with respect to x, but I can with respect to y. So it'll be 3y squared, but to balance it out, times dy dx. Plus, write down the second, y cubed, diff the first, x squared. Well, that's not a problem. I can do that with respect to x. That'll be 2x. And so that would be the derivative of x squared y cubed with respect to x. So if I want to find the equation of the tangent to a circle, this is where I guess it's useful, is I don't need to rearrange the equation of the circle. I can keep it in its implicit form, and that's why this is called implicit differentiation. Implicit form is where we haven't made one of the pronumerals the subject of the formula. So the x squareds and the x and the y's, they're all sort of mixed together. Okay, well, if I want to find the equation of the tangent, I'm going to need to differentiate it. So I will differentiate everything. X squared, that's not a problem, 2x. Y squared, I can't do it with respect to X, but I can do it with respect to Y. So I'll multiply it with respect, differentiate it with respect to Y, I get 2Y, but to balance it out, I need to multiply by dy dx, because technically what I've done is I've differentiated with respect to Y, the dy's would cancel, and I'm left with dy dx. So let's make dy dx the subject, and I end up with minus x on y. So for this particular curve, the circle, I need to substitute in both the x value and the y value to find the slope. And I guess the reason for that is that's not a function. So when I'm talking about the point x equals 1, if you think of your circle, there's two different y values. So I'm going to need to substitute in the y value as well, so it knows which particular x equals 1 are we talking about. So will I have a positive slope? Well, actually, that'd be negative, wouldn't it? Would I have a negative slope or a positive slope? So I'll sub in both the x and the y value, and I get the slope of minus 1 on 2 root 2. So there's my required slope. Point slope formula. Play around with that. Let's put it in general form. There's the equation of the tangent. X plus 2 root 2 y minus 9 equals 0. Let's say it's really exactly the same as we were doing the other day with our rates of change problems. You know, we were saying we wanted to find dv dt, for instance. We didn't have a formula for dv to t, but we did have one for dv dx, and we could multiply that by dx to t to create dv to t. Same idea. So, just a couple of questions. Remember, implicit differentiation is technically in the Extension 2 course, not the Extension 1 course. So we won't get any questions on this, but seeing we're talking about calculus, it's a convenient time to talk about it. Because as I say, it really is the same as rates of change and the chain rule. No.